Hi everyone, welcome back to Physics 142. We're getting into, for me, what is one of the most exciting parts of the course, so buckle up and hang on for the ride. So today I want to talk about the idea of magnetic induction. But to do that, first we need to review a few things. And one of the things that I want to review first is the idea of magnetic flux. All right, so let's see if we can remember what magnetic flux is. So magnetic flux, if you might remember, basically is this idea of magnetic field lines passing through a surface, right? So as an equation, we would integrate over some surface. All right, we integrate over some surface, and what we do is we take the dot product B dot dA. All right, and so what does that mean? Well, if you imagine some surface, right, or I usually like to think of that as some window or something like that, right? And we think about some magnetic field lines passing through that surface. I guess I'll do those in a different color. We'll do red for magnetic field lines. So there's some magnetic field lines passing through that surface, right? Then if I knew the area of this surface and the amount of magnetic field passing through it, then that would give me how much flux is passing through the surface, right? And remember, the area of that surface we would represent with this area vector, right? Would be a little vector coming out of the surface, right? That would be our area vector. And so we could take the dot product. The dot product tells you about the relative orientation, right? So remember, what is a dot product? Well, this is going to be the integral of B dA cosine of the angle between B and dA, right? So magnitude of B, magnitude of dA, and the cosine of the angle between them. And what does that mean? Well, that means that if, I took this surface and instead I, tipped it on its side, right? If I take that surface and I tip it on its side, and now we still have the magnetic field, here's my magnetic field, right? Well, now the area vector would be pointing up, right? There would be my area vector, and my B vectors are sideways, and the angle between the area vectors and the B vectors is 90 degrees. Cosine of 90 is 0. This would be 0 flux, and that makes sense, right? Because no magnetic field lines are passing through that surface, right? So flux just tells us about how much magnetic field is passing through a surface, and it depends on three things. It depends on how much magnetic field you have, how much area you have, and the angle between that area and the magnetic field, all right? So that's the idea of magnetic flux, and that's going to be really important for thinking about the concept of magnetic induction. But before we get there, so now I want you to just sort of keep that in the back of your mind, all right? Now I want us to think a little bit about the following question, all right? So here's flux. So now we have a question. All right, so here is a question that scientists in the 1800s, including one named Michael Faraday, were asking, all right? And the question went like this. We know that electric currents create magnetic fields, right? This is what we've been doing a lot lately, right? We had things like the Biot-Savart law, right? Remember that said mu naught over 4 pi times the integral of I dl cross r hat over r squared, right? Yes, there's the Biot-Savart law. The important thing was the electric current was creating magnetic field, right? We also had Ampere's law, where again we had the current. I guess I'll just write it down because it never hurts to remember, right? It's the integral of B dot dl over some loop, right, was mu naught times I enclosed, right? Again, it was current. All right, current is creating magnetic fields. All right, so we know that current creates magnetic fields. So then the question I have, and the question scientists had, is, well, then could magnetic fields create current? Right. So let's write that down. All right. If electric fields, not electric fields. If current, all right, if electric current creates magnetic fields, right? If electric current creates magnetic fields, can magnetic fields create electric current? All right, that's the question that we want to ask. And well, how would you test for this, right? Well, you could set up an experiment to do this, and Faraday and others set up a lot of experiments to do this. All right, and so you could imagine, like, maybe if I take a loop of wire here, right, a loop of wire, and maybe I take some bar magnet, right, and I bring that bar magnet right up by the wire, right. And so that bar magnet is then going to has some magnetic fields, right? So now we have magnetic fields by the wire, right? And then we could try to measure, maybe we stick a little ammeter here, right? Whoops. Need to label that there, right? An ammeter, right? Measures current, right? So we stick a little ammeter there and, try to measure, okay, do we get any current from that magnetic field? Or sort of another, more practical, sometimes way that people would set this up is it'll set up a little circuit, right, that looks like this, where they'll take and do lots and lots of loops like this. All right, so lots and lots of loops. All right, and if you have many loops of sort of a coil here. Remember that coils, we calculated for circles, right? For a charge flowing in a circle, you get a magnetic field that comes out through the center, right? And so if you have many loops that acts essentially the same as a bar magnet here, right? You're creating a strong magnetic field that comes out through the center. By the way, these many loops together, that gets a special name. It's called a solenoid. So if you ever hear anyone talking about solenoids, they're just talking about many, many loops together here, all right? So many loops together, that's a solenoid. And so again, you create some magnetic field, and then you maybe take another loop, right? So we'll take a second loop, there it is, right? And again, we're gonna measure, right? Put a little ammeter in here and measure the current and see what happens when, maybe we'll put a switch here, right? Put a switch in this current, and then we'll close the switch. That should create a bunch of magnetic field, and once the current's running in here, we'll expect to get a really strong magnetic field. Maybe then that'll generate some current in the blue wire. So Faraday did this experiment. Lots of people have done this experiment, and I'll even maybe try to find some videos of people online doing this experiment, since I can't actually do it for you in class when we're working online here, all right? But you can do this experiment, and what you find is no. The answer is no. You find no current flows in this wire. No current flows in this wire. You can have as much magnetic field as you want. 100 Teslas of magnetic field, and still no current in that wire. All right? So unfortunately, the answer seemed to be, well, no. All right, except, all right, it was a pretty boring experiment, right? Except there was something that they noticed when they did this experiment, all right? And what they noticed is, well, right when you close this switch, all right, right after you close the switch, right when you close the switch, you get a little spike of current. So there actually was some current just right after you close the switch, all right? You get a little spike and then nothing. Okay, so you close it, right after you close it, you get a spike of current. After, you let time go by, there's lots of current flowing through this wire, but then no current here, all right? And then interestingly, when you break the circuit again, if you open it back up, you get another little spike of current in the blue wire, all right? Or another way to think of it, as you bring the magnet up, if you bring the magnet up close, kind of fast, right as you bring it up, you get a little spike of current, all right? And right when you bring it away, you get a spike of current. But if you just hold it here, no current. And so what Faraday and others realized, all right, is that you can actually create a current in these wires. You can create a current in those wires, except that you don't do it just with a magnetic field. You do it by changing the magnetic field. All right, so that's really important. So let's write that down. All right, what we write down is that you induce a current with a change in the magnetic field. All right, I guess I'll just write it out. A change in the magnetic field. All right, induction, induce here is the word for creating that current, all right? And what needs to happen is you need to change the magnetic field. So while the magnetic field is ramping up, right when you close the switch, the magnetic field is getting stronger and stronger and stronger, and it's that change in the magnetic field that induces the current, all right? I should mention one other thing. Well, if you're inducing a current, all right, that also means that you're inducing a potential difference, right? We know that potential, V, is current times resistance, right? So if you induce a current, you also have to induce a potential difference. And so that's another important thing that we need to write down here, all right, is that induced current means there also is induced potential. All right, or sometimes people say induced EMF, right? And that's actually how this is normally written, is in terms of induced EMF. All right, so the really important and key discovery here is that it's a change in the magnetic field that produces that produces a current, not just having a magnetic field. And this actually, you are actually somewhat familiar with this probably already. For example, you might know that, when you take a credit card that has a magnetic strip on it and you put it in, the slot at like a gas station, if you just put your card in, nothing happens, right? It always says what? Remove quickly. Right? It's the action of changing the magnetic field, right? That little magnetic strip, it needs to be moving, it needs to be changing. That's how you actually induce a little current in the card reader. It's through the changing magnetic field. If you just put the card in, there's no change in the magnetic field, and therefore nothing's going to happen. You have to actually pull it out, right? When you pull it out, then you're changing the magnetic field. That's what creates a current in the card reader, and then it recognizes your card, all right? This comes up a lot in electric generators. We'll get to this, all right? And this is really, really important, because what this is you'll notice there's no actual contact between these circuits, right? So here I have a magnet. It doesn't actually ever have to touch the wire, right? This wire doesn't have to have a battery on it, and yet you're getting a current in it. So, wireless charging, that's all due to the fact that you induce a current with changing magnetic fields, all right? And so this ends up being really, really, really powerful and is extremely important to understand, all right? But it's the change in magnetic fields, not just having magnetic fields, that creates current. Now, of course, we want to be a little bit more mathematical about this, all right? And so to be a little bit more mathematical, that we do that with this thing called Faraday's law, all right? So Faraday realized, so Faraday was the scientist who sort of first realized this, all right? And so what Faraday realized is a couple of things, all right? He noticed that, first of all, how much current you got, all right? Or how much V, or remember V, he actually wrote it down. Usually we would write this down in terms of EMF, all right? So induced, all right? The EMS induced, he realized that it was proportional to the change in the magnetic field, right? ddt, right? The faster you change the magnetic field, the more potential you induce, all right? That was one thing he noticed. But it turns out that it's not just the change in how much magnetic field you produce. If you have a bigger loop, all right, or if you make the loop bigger, it actually also is proportional to the area. And it also turns out it depends what angle you put the magnetic fields, all right? If you change the angle here, if you come with the magnet in at an angle, all right, also is proportional to the angle. And well, magnetic field area and angle, those quantities, we've seen all those quantities combined together before, right? That's the idea of magnetic flux. And so it actually isn't just changing magnetic field that matters. What really is important is it's changing magnetic flux. And so let's write this down here, all right? I think I need a little more room, so we'll just move the board up just a little bit and make sure everything is still working here, all right? So what Faraday's law said, and we'll write it, I don't know, in a different color here in red so that we get it, because it's really important. What Faraday said is that the EMF induced, all right, that is, I times R, or the potential that gets induced, all right, ends up being minus, and we'll think about what that minus sign means in just a second, all right, ddt of the magnetic flux, all right, the time derivative of the magnetic flux, all right. This is Faraday's law. This is one of the most important laws for our economy today, all right, physics laws for our economy today, that if you change the magnetic flux, then you get a potential difference in that wire. You get a current in that wire, all right? Now, I should just note a couple of things about this, all right? So, ddt of the magnetic flux, we could also write that as minus ddt. Magnetic flux is the integral over a surface, right? We just did this, of b dot dA. So we should note that, right? And it's really important to note this is a time derivative, but an area integral, right? So this integral and derivative don't cancel, right? Because you're taking a time derivative, the derivative with respect to time, whereas the integral is over area. And just really to show that, right? Well, let's take that dot product, right? So minus ddt of and let's make sure that you can still see this. Yep, okay, all is good. So it's minus ddt of the integral of b dA cosine theta, right? And if you just imagine for a second, let's imagine that we have, some, we're thinking about magnetic flux through some circuit, right? Through some loop, right? And we've got magnetic field coming through there. If the magnetic field is uniform throughout the area and all at the same angle, then we could pull b and cos theta out of this integral, right? So we could do that. Then that would be minus ddt of b cos theta times the integral of dA, right? And the integral of dA, well, that's just the area of the thing, right? That's just the area. And so if you have uniform B over the area and the angle is all the same everywhere, all right, if that's the case, okay, then we could write this. So maybe we write if B and theta are constant, okay, if B and theta are constant, right, this is going to be minus ddt of B times A times cosine theta. And so importantly, there are three things this depends on, right? It depends on the change in your magnetic field, the area, right? Or you could imagine changing the area, right? And it depends on the angle, or you could imagine changing the angle, right? So if you have a constant magnetic field, but you're always changing the angle, all right, that would actually change the flux, and that would then induce a current and induce an EMF. So that's really cool. Now this minus sign, all right, why the minus sign? Okay, well the minus sign actually has to do a little bit with the direction, okay? And the idea here is that this induced EMF or this induced current always is going to oppose the change. All right, is what we say. We say it opposes the change. And well, what does it mean to say that it's opposing the change? Well, I'll go into that in great detail in the next video. All right, but just to get sort of a rough idea of this, all right, if you imagine that I have some current loop, all right, so let's just draw a little, here's some loop of wire here. All right, and then I put a B field through this wire, we'll say coming out of the page, and we're going to increase it. So we'll say delta B is coming out of the page because I'm increasing the magnetic field, all right? So we're going to increase the magnetic field, all right? Now you might imagine, then if delta B is coming out of the magnetic out of the page, right, normally we would expect current for magnetic field out of the page to be counterclockwise, right? That would be sort of our expectation for out of the page current. But what you'll find is that the induced current, all right, actually goes opposite of that, all right? This would be I induced, all right? It's actually, whoa, you can't read that right, all right? Let's try that again. I induced. All right, I induced actually goes the opposite direction from what you might expect, all right? And so we will go into that in more detail in the next video, but hopefully you get a sense that this is really cool, all right? Because now we're able to create current in wires without ever actually touching the wires, all right? And we do it by changing the magnetic flux.